Good morning. Are you ready for the course to almost be over? I sure am. We ended last class in the middle of an example of the insert operation for AVL trees, so we're going to continue that. We began by inserting the key 5 and started by executing the usual insert operation for a binary search tree. So we basically searched the tree and inserted 5 at the position where this search would find it if it existed. This changes some of the node's heights, and we note that the only nodes whose height have changed exist on that path to the node that we just inserted. So 4's height went from 0 to 1, 3's height went from 1 to 2, 6's height went from 3 to 4, and did 10's height change at all? 1, 2, 3, 4. I'm thinking it didn't because these nodes exist and we're already at the same level, but I just want to make sure this is consistent with what I've written down for all the other nodes. Okay, 6's height went from 2 to 3. That's better. I'm just going to rewrite this to more clearly show the change in each node's height. Yeah, so notice that all of the nodes whose height changed are on that path. Something like 15, its height didn't change because nothing was added below it. Additionally, every node's height that did change changed by only 1. Since this was an AVL tree before, the balancing factor of each node was either -1, 0, or 1. So if this change caused a node to be unbalanced, and I'm pretty sure it did, 6 is looking kind of unbalanced right now, it made it so the balancing factor is just plus or minus 2, because it was from -1 to 1 and only changed by plus or minus 1. So we're going to algorithmically update those heights, sort of formalizing the procedure that I just did of changing these values. We start at the node that we just inserted and move up the tree, updating the height field as needed. The new node has no children, so it's balanced. And then we proceed upward from child to parent until we encounter a node that's no longer height balanced. So the new node had balance factor 0. This node isn't explicitly stated to have any balance factor, but it has balance factor 1. Right height minus left height is 0 minus 1 equals positive 1. And then node 3 has height 2, 1, 2. And its sibling, node 8, has height 0. This means that the balancing factor of 6 is 0, right minus 2, left, equals -2. It's unbalanced. And you can see this visually. The left side just goes on for more than one node longer than the right side. So let's try a rotation. This is going to bring 3 upward. It's going to take 6's place. And then 6 is going to move downward, and 8 is going to stay as the right child of 6. Oh yeah, and to avoid a situation where 3 has children, its right child is going to move to become the left child of the original top node's right child. Did I say right? I meant it'll be the left child. Just look at this. So in case you're confused, because I sure confused myself trying to list the steps, the algorithm for tree rotation is detailed earlier in the lecture. But I should note, you don't have to memorize this whole thing, like promote y to replace x, demote x to be the right child of y, assign y.right to x.left. Don't have to memorize that. I sure didn't. You just need to know how to do this. And if it sinks in, wait, what slide was I even on? Yeah. And if the way to do this operation sinks in, you'll kind of forget the explanation, and that's okay. Try explaining to someone else how to walk. You can't do that, just know how to walk. So you should know how to do rotations. The result will look like this. And now, finally, you'll notice that this didn't work. Let's see. Oh yeah, this didn't change the balancing factor at all. Well, I guess it probably changed it to a negative to a positive. Before, this node that we noticed was unbalanced, had a balancing factor of -2 because its left side was 2 longer than the right side. And now all we've done is make it so the right side is 2 longer than the right. Its balancing factor is now 2 minus 0 equals 2. Well, that sure did something, except it didn't. This is the case that I was alluding to last class about how tree rotation can sometimes fail. I was totally confusing it with something else when I said that it can mess with the binary search tree property. Because as you can see, the property is still preserved. All of the left children are less than their parents, and all the right children are greater than their parents. The failure here is that the tree rotation didn't result in the tree being balanced. So what do? We're going to go back. In this case, we need to use a technique called a double rotation. You can tell when you need to use a double rotation when you attempt a single rotation and it fails. So the algorithm that should be in your head and would be in code is to attempt a single rotation, check the tree balance, and then attempt a double rotation if needed. What's involved in a double rotation is rotating the unbalanced side of the thing we're rotating. So last time we did a rotation around node 6, and that didn't work. So now we do a rotation around the side of the tree where the most nodes are. like where it's unbalanced towards. And then this slide's picture of it is a bit misleading. It kind of looks like we're rotating around 4, and like we're going to end up with something like this. But that's not very helpful, and more importantly, it's not what the slide's doing. We can see here that we're promoting 4 and demoting 3. So that's actually a left rotation around 3. So you can disregard these red arrows. And then you just do the rotation. The intuition should be starting to set in now, hopefully. You can maybe use the algorithms listed here as like training wheels, but eventually you should be able to just imagine 4 going up, 3 going down, and then some nodes being shifted side to side if necessary to avoid a case where a node has 3 children. In this case, though, we don't do any of those side-to-side shifts. It's just as simple as 4 goes up, 3 goes down. And we end up with something like this. Don't think about that 6 for now. Just observe. Can I even show them both at the same time? Barely. We rotated that part of the tree. 4 went up, 3 went down. After we've done that rotation on the unbalanced side of the tree, we reattempt that first rotation again. And then it works. We demoted 6, promoted 1, or demoted 6, promoted 4, and then also this 5 moved to become the left child of 6. Ta-da! And we can also see that no more nodes need to be rebalanced. It is possible for a case where there needs to be more than one rotation as you go up the tree, I think. But that's the insertion algorithm. I'm going to attempt this example and just go as far as I can without having to do any major redrawings of the tree. So first we're going to insert the key 18. First step is to do the good old binary search tree insertion algorithm. I'll rush through this because y'all are probably amazing masters at it. 18 is greater than 10, greater than 15, less than 20, greater than 17, less than 19. So it's going to go right here. And then we can start to see that the right side seems to be a lot longer than the left side of this tree. But let's go upward and check each node's balancing factor manually. So 18 has a balancing factor of 0 because it has no children. Slightly more formally, you could say that both of its children are non-existent and thus have a balancing factor or height of -1. And then 18's balancing factor is -1 minus -1, which is 0. And we arrive at the same result as we would get from the intuition that a node with no children must be balanced. Moving up, 19. That has a left child of height 0, not to be confused with its balancing factor. And then its right child doesn't exist, so we say it has height -1. Calculate the balancing factor, -1 minus 0 equals -1. That's fine. 17. I'm going to have to figure out a consistent way to draw this to avoid confusing the balancing factors and the heights. I think I'll take away these calculations. I'll still draw them. I'll erase them soon afterwards. And then this is a convention I just invented. We're going to draw the balancing factor on the bottom and the height at the top. So 19 has balancing factor -1 and height 1. 17 has height 1, 2. And its balancing factor depends on its right child having height 1 and its left child having height -1. We end up with a balancing factor of 2, which is bad. By definition of AVL trees in balance, we found that node 17 is unbalanced, so we need to do a rotation around it. Am I going to be able to draw this? I think I'll just draw the subtree again in the corner. When you're studying this, I would recommend just having a scrap paper, copying the entire AVL tree to that paper, and then erasing as needed. So it's balanced or unbalanced towards the right side. So we're going to do a left rotation to bring it back to balance. So we will first give ourselves some more space. Promote 19, demote 17. And then what happens next is a little weird. You might be inclined to make 18 the right child of 19, but 18 is less than 19. It shouldn't be on the right. So this would be wrong. Luckily, this isn't some sort of failure of our algorithm. This is just a mistake that I have made in the past and wanted to point it out, so hopefully you don't. The algorithm for rotations, you may remember, involves moving this left child to become the demoted node's right child. So we'll end up with a subtree that looks like this. This does preserve the binary search tree property, but it doesn't fix the balancing issue. Node 19 still has a much longer left subtree than it has the right subtree, and basically this has done nothing. This is a sign that you need to do a double rotation. Ooh, I just realized that I have a ton of space along the bottom. Cool. So I'm drawing a big X because it's wrong. And then we're going to revert back to the original subtree. And do a double rotation. So this means going a node downward into the side, like the longer side, in this case, the right subtree, and then doing a rotation around the unbalanced node's child that has a larger height. So we're going to do a right rotation around 19. 17 will stay right where it is. And then this rotation is very simple. Follows the same rules as before, but since it just involves two nodes, it's very intuitive that you just bring 18 up and then 19 down to reflect it. So this was the first rotation of the double rotation. The first failed rotation doesn't count. We only say that we've done one rotation so far. And now the next part of the double rotation is to attempt to rotate around 17 again. So this will involve promoting 18, demoting 17, and then like if 18 had a left child, we would move it to become 17's right child, but it doesn't, so we don't. 19 just stays right where it is. And look, that subtree is balanced. You could imagine this whole thing taking up this whole space. This is quickly getting super cluttered, so I apologize. But you basically have the 18 here, 17 here, and actually 19 would stay where it is. Cool. Okay, I think I am not even gonna attempt the others. Actually, let's see if they're simple. If I have to like overlap anything in here, I'm just gonna give up though. Insert 22. That would go right here, and by the rules that I just established, I'm going to give up now. You could do the rest yourselves, though. The answer is right here. Just as we saw after inserting node 18, node 17 is rebalanced using a double rotation. No mention of node 22. And I suppose that, yeah, after we insert 22, it wouldn't increase the height of the tree at all. So there wouldn't be any rotation needed. But then after inserting 32, it would go right here. And that would require a pretty intensive rotation. It would follow all the same rules as rotations before, but it would just be a bit intimidating because you would have to go rather far up the tree before you find that unbalanced node. I believe it would be 15. So you would promote 20, demote 15, and then move 17 to 15, I think. Yeah, that tracks. The only issue, or the only incorrect part of my explanation right there is that you wouldn't move node 17 to 15 because that previous rotation brought 18 to 17's place. But other than that, it was fine. So let's analyze this operation a bit. So assume that X is a node in a binary search tree and that the subtrees rooted at each of its children are both AVL trees, and the heights of those subtrees differ by 2. These conditions might seem arbitrary, but this is describing a situation where we had just inserted a node. And then we just inserted a node in a way that made it unbalanced. Yeah.
We use the double rotation when we're at a leaf long and it alternates parent, like right child, left child.
Yeah.
Is that true for everybody? They alternate from that order?
I don't know. You're certainly right in describing the situation that we just went through, but I'm not sure if it applies in general. I recommend just using this sort of algorithm of attempting a single rotation, and then if it fails, reverting and doing a double rotation. Yeah.
Sorry, and when it comes to rotating, other than just like seeing the numbers, like what are you doing to determine which direction you should be rotating? Is it have something to do with the balance factor?
Yeah. I'm just going to scroll up the slides to look for a cleaner picture than this one. Yeah, this is a decent example. Basically, you should rotate into the unbalanced side. So in this example, actually it's ambiguous what I mean by the unbalanced side. You should rotate into the shorter side. So in this case, the left subtree is much longer than the right. So we want to restore balance among those. So we rotate towards the right, giving more height to the right and less height to the left.
Does that mean that it can just kind of be determined by like the sign of the balance factor?
Oh yeah, definitely. Like, when I'm doing stuff like this, I sort of just look at it and evaluate it visually. We're rotating into the short side. But if it helps, you certainly could focus on the sign. And also, if you're writing code for this, like that would definitely have some sort of if statement based on the sign of the balance factor. Okay, and then this actually addresses something I was unsure about earlier. We just state, not prove, that after inserting a node into an AVL tree, at most 2 rotations in total are required to rebalance the tree. So as you're moving upward through the tree and rebalancing nodes that are found to be unbalanced, you'll only ever have to do at most 2 rotations. That's pretty neat. From this, it follows that the insert operation for AVL trees requires big O of log n time. This is because, I'm just looking for this slide where we had just inserted something. Okay, so with the insert operation, first you do the binary search tree insert. That takes O of log n time. And then you travel up the tree, just one path from a leaf back to the root, and following from our discussions about the height of the tree. The height of a balanced tree is big O of log n. So moving up the AVL tree will also take big O of log n. You'll have to do at most 2 rotations along the way, but each rotation takes constant time. It's just a specific number of operations to rebalance one node. So with all of those in mind, the insert operation for AVL trees requires big O of log n time. This will probably take slightly longer in practice than the insert operation on a binary search tree. You could quite easily tell from the fact that the algorithm is do the thing for the binary search tree and then do some other stuff. So obviously it'll take longer than just doing one thing. But they have the same asymptotic time complexity. So in practice, the difference in execution time between them is gonna be like seconds at most on like a huge data structure. Okay, now for the delete operation. And this is kind of going to be finicky. Like, it's already finicky with binary search trees. But it follows the same sort of ideas as the insert operation. We first use the corresponding algorithm for binary search trees. And then we note how the tree has become unbalanced and move up the tree, rebalancing along the way. So let's delete the key 8. In a binary search tree, this is just the easy case. We would somehow access node 6 and then set its right child pointer to null. And then the Java garbage collector will recognize that 8 is garbage and delete it. So that's our first step for the AVL tree deletion algorithm. But this will possibly cause the tree to become unbalanced. We figure out whether it has by moving upward through the branch containing the node we just deleted up to the root, and updating the height field and correcting unbalanced nodes as needed. So we start our journey going to 6. We find that its balancing factor is -1 minus 1, which equals -2. And it means that this node is unbalanced. So we need to rotate it. As discussed earlier, we sort of rotate into the smaller side. We can also see that since the sign is negative, we have to do a right rotation. And the rotation itself is rather simple. Promote 3, demote 6. Those are the obvious parts. The tricky part is that if we only do those two things, then 3 will have 3 children. So we just need to move 3's right child to 6's left. Ta-da! And now this branch is balanced. You could tell by checking its balance factor again. 1 minus 0, right minus left. That's just 1. Falls within the range of acceptable values. And so we're done. Now, that was an example where we needed 1 rotation, but there are cases similar to what we saw with insert, where there might be more than 1 rotation needed. So in this example, we're going to find a key k such that deleting k from the tree requires more than 1 node to be rebalanced. So let's think about what that key is. If you're doing this yourselves, the best strategy for this is probably just going to be trial and error. delete some keys, and hope for the best. But intuitively, I sort of want to delete a key that makes the tree look really unbalanced. And 1 is sticking out to me because if we delete it, we'll be left with 3 being unbalanced because it has 2 nodes on the right, 0 on the left. Balancing factor of 2, very bad. And then rebalancing that will result in a subtree that looks like this. Yeah. And then this whole left subtree will still be significantly shorter than the right. It's only going to be height 1, while the right subtree is going to have height 3. So again, intuitively, I just recognized that I wanted to make the tree be really unbalanced, and I noticed that removing 1 would actually make the left subtree even shorter and thus make the whole tree really unbalanced. So, draw the end result of deleting this key. Well, we already acted out the deletion and resulting rotation from deleting 1. We would have, deleted that, moved up the tree, notice that 3 is unbalanced, and the rotation. And then, after that, the algorithm would continue. We've successfully balanced this node, so we would move up to the root, and we would check out the balancing factor of each of its children. So 6's height is 1. 15's height is 1, 2, 3. Oh, wait. I'm just drawing the values up there to adapt to what I remember of the rule I made up earlier. So 1 and 3 are very far apart, obviously. But then we could just double check, calculate the balancing factor. 3 minus 1 is 2. Uh-oh. The root node is unbalanced. The entire tree is unbalanced. So we need to fix this. We're going to do a left rotation. This might get a bit weird because of how I've been scratching out and replacing values, but I'm gonna do my best. When you're in a situation, when you're in a quiz or the exam, you're going to have much more space to draw on than I do, and you're going to have an eraser. So take advantage of both tools and don't do stuff like this. Okay. So, left rotation. 15 gets promoted to 10's place. 10 gets demoted down to 15's left child. And then, can I rotate this? No, never mind. If we only did those 2 steps, node 15 would have 3 children, those being 10, 13, and 20. So, the last step is to make 13 into 10's right child. And there we go. So we deleted 1, and as the slide so nicely says, both the parent of 1 and the root node had to be rebalanced. So in general, you might need to rebalance big O of log n nodes, but it still requires no more than 2 tree rotations to rebalance each node. So basically, you'll have to do either a single rotation or a double rotation. No such thing as a triple rotation or further rotations. So since you do the familiar O of log n BST deletion algorithm first, and then move up the tree, doing up to O of log n rebalancing operations, and rebalancing operations go in constant time, this all comes together to say that the revised delete algorithm requires O of log n time in this case. So although the AVL tree algorithms are more complicated than their binary search tree counterparts and will take a little bit longer like in terms of execution time, they're sort of in the same speed class. And so when the number of things that you're storing in these data structures gets humongous, AVL trees and binary search trees will have basically the same performance. I think this is the last example. We're going to check out the annoying case in which the node to be deleted has 2 child nodes. We're going to demonstrate this by deleting key 15. And you'll remember from binary search trees that this is the hardest case. And for AVL trees, it technically is too. But I guess the gap of complexity isn't that much bigger. Like, what I'm saying is that with binary search trees, deleting a node with 2 children was significantly more complicated than deleting a node with 0 or 1 children. Now, you'll have to go through the same procedure, so it is a bit more difficult, but the stuff that happens afterwards with tree rotations is no different. So in terms of AVL trees, deletion of nodes with 2 children isn't that much harder than deletion of nodes with 0 or 1 children. Whew. So hopefully you remember the binary search tree deletion algorithm for this case. We have to find the successor of the node to be deleted. And in this case, the node has a right child, so the successor is the minimum value of the right subtree. If we were writing code, we would find it by first accessing the right child and then moving left, 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 left until we find a node with no left child. In this case, we find it pretty much instantly. Since finding the minimum involves going left until you find a node with no left child, feels obvious now that I've explained it up to this point, but this node can't have a left child. And thus, after we swap the node with its successor, we can just delete it as in the easy case. So we delete 15, promote 19 to take its place, and then no rebalancing is actually required. So in this case, the delete operation still takes O of log n time. So you might have to find the successor of the node, where the worst case for this is having to go down the entire height of the tree. Swap, which takes O of 1 time. And then the rest of the algorithm works the exact same as in the other AVL tree deletion algorithm cases, which is to say it takes O of log n time. So we see that we see that deleting a node with 2 children takes O of log n time. And we saw earlier that if a node has 0 or 1 children, it also takes O of log n time. So the delete operation takes O of log n time in all cases. It's nice. Keep in mind that this is regardless of the order of insertion of elements. So with binary search trees, those operations took O of log n time as long as the data structure was configured nicely, as long as the tree was balanced. But these rules about rotation guarantee that the tree is always balanced. And thus, the algorithms take O of log n time all the time. Sick. We're done. I think the UM Learn site has slides on heap sort, but like, who cares about heap sort? Am I right? I don't remember how much I said about it, so apologies if I'm repeating myself. But there's one more lecture in the course, and it covers a sorting algorithm that uses a heap. It's actually kind of neat. You basically take the array that you're sorting, turn it into a heap, and then sort it just by calling retrieve max over and over. The heapify part takes place in linear time because it involves doing a few operations for every element of the array. And then remember that retrieve max takes O of log n time. So do that for every element of the array, n times. And then the sorting part can be done in O of n log n time. Pretty neat. But I can't really think of any possible quiz or final questions for this. What I'm gonna do, ask you to execute heap sort on a piece of paper, ask you to parrot back to me in time complexities. Both of those are kind of boring. So I'm just gonna skip this. So that brings us to the most exciting topic in the course, final exam prep. And I'm not sure exactly what to display here. Let's go to UM Learn.
Can you talk about what's covered in quiz tomorrow?
Oh, totally. Yeah, sorry. Final exam prep is the second most exciting topic in the course. Let me pull up the quiz. It is basically finalized right now. But I'm still thinking really hard about that programming question.
Will there be a post on UM with the full details of what's going on with this?
Yeah, I could do that again. I think that was really useful last week. So looking back, I totally should have done it every time, but I still have some room or time to improve. So yeah, I can do that for the last quiz. Let's see. Okay, the quiz is totally not finalized, but I can still talk about what will definitely be on it and what will probably be on it. And I'm gonna write it down because this is the medium I'm using to do the lectures, but I'll do an announcement on UM Learn with typed out details. So the quiz will definitely have questions about graph traversals. And Dijkstra's algorithm. How's that? IJ or JI? In the quiz, it's spelled IJ, so if I got that wrong, I'm just carrying that error forward. Okay, so these two topics will definitely appear on the quiz. Oh wait, one more thing. AVL tree. Insertion. So definitely study these three topics. I do have to keep the questions a little bit secret in order to preserve the point of a quiz. Because if you knew the questions in advance, you could just study those questions specifically, memorize answers without actually learning anything. No good. So I have to keep the details of the questions kind of mysterious, but if you want clarification on the nature of the question, you could definitely ask me, and I'll give as much of an answer that I'm prepared or that I feel comfortable giving without compromising the educational integrity of the quiz or whatever. Yeah. And then, gonna say probably for other topics. More of a maybe, but I still want you to study it just in case. So the quiz will probably have questions about graph. How should I say this? Graph definitions. / graph drawing. I wasn't sure what word to use, so I decided to just use both. I have some questions written out already that ask you to draw graphs that have certain properties. For example, having a path of a certain length. So you need to know the definition of a path in order to effectively draw these. But I'm questioning whether to include them because I'm not completely sure that these are very useful for our study of graphs. Questions I have put together so far would be certainly useful in a graph theory course where you are learning about graphs for the sake of learning about graphs. But this is a computer science course. We're learning about graphs for the sake of being able to write better programs. And admittedly, not all of the definitions that I went over last class really work towards that goal. So questions where you have to draw graphs with certain properties might appear on the quiz. And then, you're waiting for this, the programming question. I'm putting both of these under the header probably, but graph definitions is maybe, and then programming is almost certainly. I have a programming question written out, and I'm only going to remove it if I panic and go like, oh, this quiz is way too hard as is. And because of the uncertainty around it, I don't want to talk any more about what the programming question is going to be about, but I'll be happy to talk about how it will be structured. Because last time I taught the course, there weren't any programming questions on the quizzes at all. And then a whole bunch of students got absolutely cooked on the programming assignments on the final exam. So I wanted to sort of help you prepare for how those are going to be written. And also the reasons why students did so badly on the final exam programming questions are things that I'll go over when we move on to exam prep. Which I suppose we can do next. Does anyone have any questions about the quiz before we move on to talking about the exam? Yeah?
Wait, so we're not just gonna be able to know what like data structure or I guess maybe this like
Yeah, like what topic
Yeah.
we're covering? Yeah, like I am considering taking or making the programming question be about something that we haven't covered this week. Basically make it so you have to start studying for the exam now. But in exchange for that, not making it too difficult. Or I might make it about AVL trees or graphs, things that you're going to be studying in the short term, but make it more complicated as a result. Not sure. Anything else? Yeah?
Just AVL and cert
Oh yeah. I totally forgot to put that right here. That's to say, I have a question drafted about inserting things into AVL trees. I don't have one about deleting things from AVL trees, but like that's part of the material and easy to make a question about, so I might include it on the quiz. Yeah?
programming question. There's no chance we're gonna get back our test or our previous quiz that we did a programming question before we rank that one.
Oh, you haven't gotten that yet? Do you remember which number quiz that was? Like, was it quiz 3, 4, 5? Okay. I'm gonna check the grader's progress on that on CrowdMark because, yeah, it would be super useful if you got programming question feedback before the next programming question. Okay. Progress is looking good. There's going to be like 1 or 2 things I'll have to follow up about, but I'm going to put that on my to-do list to do today because I actually didn't realize that you didn't have that yet, and I agree that that would be really helpful for studying. So send out quiz 4 grades due today. Anything else? Also, this will be posted online. No need to take a picture of it. Yeah?
We have a rough as to when we're gonna get our second assignment.
Oh yeah, second assignment is finished grading. I just need to report a small handful of academic dishonesty cases. That just keeps getting pushed down the backlog, but I understand how frustrating it is to not get much feedback for a course, especially this far, like this close to the end. So I'll prioritize that. I think I'll have to further procrastinate on evaluating regrading requests in order to get those done, but I think new assignment feedback is more important than grading requests, so hopefully that's not too bad of a trade-off. I feel like I'm back in undergrad, like taking way too many courses at once, but it's just one course. Huh. Okay, anything else? Okay, let's talk about the final. So I uploaded some stuff about the final right before this class started. It's currently set as hidden, so you can't see it, but I will unhide it very soon. The only reason that it's hidden right now is because, like, how much detail should I go into this? It's the end of the term and I'm kind of stupid. I forgot my headphones today and wallet yesterday, and like I'm totally in the kind of frame of mind where I might accidentally upload the final to UM Learn. So I just uploaded these before the class, and then during my office hours, or right after if I'm chatting with students the whole time, I'm going to just double check that I actually uploaded the files that I thought I did, and then make these visible. These file names sure do check out though, so I think I uploaded the right files. First thing I wanted to go over is to attempt to preempt some questions that I was asked several times during the previous term's exam, and also help you avoid the mistakes that students last term ran into during the programming questions. So a big part of the difficulties last term with the programming questions is the fact that they take a sort of different format from anything found on the assignments. On the assignments, you would build new data structures from scratch, and programming questions on the exam had you use existing data structures to solve problems. Both of these are valuable. Learning or taking time to make your own data structure. Making your own data structures helps you learn the ins and outs of those data structures, makes you really familiar with their advantages and disadvantages. Whereas questions about using data structures is more applicable to the type of data structure work that you're going to do in the real world. I apologize for the lack of the second type of question on the assignments. If I were starting this course again from scratch, like making my own assignments again, I would include some questions where you're like, here, you can use Java's built-in hash table. Now do something cool with a hash table. But I can only make so many assignment questions. The programming questions on the final exam last term were more that second kind. You can use data structures without re-implementing them, and you have to do something smart with them to solve a problem. And that kind of caught students off guard. I don't blame you guys because it was different from the assignment content. Got a lot of people going like, do I have to like make a hash table? No. You'll be told what you have to do on these final exam programming questions. There's actually going to be a mix of both. Like last term, it was all using data structures. This term's exam will have a mix of making data structures and using them. making data structures you're already familiar with from the assignments, so I won't go into too much detail for this. But using data structures is less familiar, so it's worth going into more detail about this. You'll be evaluated on data structure choices. You've already done a bit of this at a high level from that one quiz question where you had to choose between like an array, a linked list, and sorted or unsorted variants of both, given some business requirements. This will be a bit more grounded, like you just need to choose data structures that'll make the algorithms you're writing most efficient. Like, can I think of a decent example? If you're writing a question that involves looking up a bunch of information, using a sorted data structure would get you more marks than using an unsorted data structure, and using a hash table would get you more marks than either of those other options. You're allowed to use any of the ADTs taught in class. And to that effect, I want to give the quiz or the answer to a question that I gave the most during the final exam. Basically, you can just pretend that you're using Java's built-in data structures. Like, if you're given a question that's like, use a stack to model this situation, that was vague. Use a queue to make an algorithm for modeling lines at a grocery store. I don't know, that's slightly less vague. If you're given a question like that, you can just use the stack or the queue. You could make objects, call, push, pop, and queue, dequeue, all that stuff without implementing it yourself. I feel like I'm kind of talking in circles, but I want to make sure I don't miss anything. So I just want to reiterate, there will be a mixture of questions where you have to make data structures and when you have to use data structures. And you will be told for each question what you have to make, and then anything not mentioned you can use. And then all these bullet points tell you like things you could use with certain ADTs, but I think these are just sort of there to jog your memory if you already know the interfaces for each ADT, and isn't really a very good cheat sheet on its own. So if you haven't yet, I definitely recommend internalizing, maybe even memorizing the available operations for all ADTs. For example, I don't know, stack has push, pop, and is empty. Queue has enqueue, dequeue, and is empty. Tables have these add based on index methods. They also have delete and search. Priority queues, implemented using heaps, have remove max and insert. So like, you should know all that stuff. Know what operations each ADT has, and yeah, just what it can do. Also how quickly each ADT can do each operation. You don't necessarily have to memorize a bunch of time complexities, but you should have an understanding of ideas such as inserting something into a sorted array takes longer than inserting into a sorted array, or hash tables have constant time search as long as there aren't too many collisions, things like that. Oh yeah, this is funny. Not every ADT has every operation, so remembering what these things can do is as important as remembering what they can't do. So if you have a question involving a queue, don't even think about calling pop on it, because that's not how these things work. You have to follow the interfaces of all the things you're using. And finally, my favorite disclaimer, your code does not need to be syntactically perfect, but it should be clear that you are trying to write Java code. And then last thing is this formula sheet. In case it wasn't clear from the file name, the last 2 pages of the final, I actually made this document by opening up the final in a PDF viewer and then deleting all the pages except for the last 2. So all of this is stuff that you can be assured that you don't have to memorize. You'll be able to refer to these things during the test. Of course, you'll need to understand what each is doing and where to use it, but I'm taking the grunt work out of it. So I will unhide this as soon as I convince myself that finalpractice.pdf is not final.pdf. And then I could go over these practice problems next class as well. One more thing I wanted to mention, not that important, but I thought it was neat. The final exam is going to have its questions ordered in the same order that you learned the things. So all the first few questions are going to be math-based. The last few questions are going to be graph-based. And then there's going to be a proof and a couple programming questions in the middle, which is kind of a hint about what those programming questions are going to be about. I've said too much. Okay, if you have any questions in the last few minutes, ask them, and then if we run out of time or the questions die out, you'll be dismissed. But let's see, 2, yeah?
You mentioned the questions will get some, do we have access to the marking rubric for programming questions?
Oh, yeah.
Just to see what you guys are kind of looking for and whatnot.
Yeah, I could describe the rubric because it's not actually that specific. I'm going to tell the markers to start at the maximum point value and then deduct points for every mistake. So if the question involves printing out some items in a specific order and there's a small mistake in that order, you might get 1 mark off. And then if you're just not doing what you're asked to do, you'd get most of the marks off. There won't be a specific rubric because these programming questions are much more open-ended than other short answer questions we've seen. And did you have a question?
In case that we get another asymptotic conference, would it be like the quiz where we get the relevant ones required?
Yeah, definitely. Yeah, they won't show up on that, on those last 2 pages because there were 5 pages worth of properties. But yeah, if there is a question about those, all the facts you need will be given on the same page. Yeah?
Are there entity level elements now?
Not sure if I even want to answer that because that might be going too far into format of questions. I don't know. Ask me again tomorrow, and between now and then, I'll try and figure out how much detail I want to go into on what the questions are. Anything else? Cool. You're dismissed. See you tomorrow.